One of the first places in mathematics that we encounter complex numbers is in the context of using the quadratic formula. So let's say we look at a simple quadratic like x squared plus x plus 1 equals 0. This does not have real solutions, it does not factor. But if we use the quadratic formula, a is 1, b is 1, c is 1, the quadratic formula and a little bit of simplification is going to yield the two roots minus 1/2 plus root 3 over 2i and minus 1/2 minus root 3 over 2 times I. Every complex number can be written in the form a plus bi. We refer to a as the real part and b as the imaginary part. We use the notation capital C to denote the set of all complex numbers. So this looks kind of like the symbol for the natural numbers or for the reals, except we use a C instead of an N or an R. Every real number is also a complex number. For example, z is equal to 3. The real part of z, which we denote using the notation re, is equal to 3. The imaginary part is in fact equal to 0. Graphically, we represent complex numbers using what is known as the complex plane. This is very much like R2. So for example, 2 plus 3i. We label the complex plane, we label the horizontal axis, or what we usually think of as the x-axis, we label that the real axis, re, and the imaginary axis we label as im. And then we plot the complex number z. We typically use the letter z by marching 2 units in the x direction, or in the real direction, and 3 units upwards. So in this case, the real part of z is 2, the imaginary part of z is 3 for this example. Some other notation. We put absolute value symbols around z to denote the distance from z to the origin. And we're not going to usually say absolute values. We're going to say words like norm, or more typically, I use the term modulus, the modulus of z. So in the picture above, the modulus of z by the Pythagorean theorem would be this distance right here, which would be the square root of 2 squared plus 3 squared, which simplifies to be the square root of 13. Another important notation is what's known as the complex conjugate. We put a bar over z. The complex conjugate is simply what you get when you take something like 2 plus 3i and you switch the sign of the imaginary part from, let's say, 3 to negative 3. And the effect of taking the complex conjugate graphically in the complex plane is that we are reflecting about the real axis. So the conjugate, if we look at z, it was 2 plus 3i. Its complex conjugate would be 2 minus 3i, which would be down here. That's merely the reflection about the real axis. In general, if we have a complex number a plus bi, the modulus of z is the square root of a squared plus b squared, and the conjugate of z would be a minus bi. Every complex number can be written in the a plus bi, or what we call the rectangular form. Let's take a look at a couple examples. Z is 2 plus 3i, w is 1 minus I, the product of z and w. 2 plus 3i times 1 minus I. We can distribute using the distributive properties, and we would get 2 minus 2i plus 3i, and then minus 3i squared. Using the fact that I squared is equal to negative 1, this will simply be positive 3. So we'll have 2 plus I plus 3, which is 5 plus I. Another example, z over w. We can write this in the rectangular form a plus bi as well. And the way we do that is we multiply by a form of 1 consisting of the complex conjugate of the denominator divided by itself. In this case, it would be 1 plus I over 1 plus I. Let's expand. The numerator will be 2 plus 2i plus 3i minus 3i squared, or plus 3i squared. So that's going to give us 2 plus 2i plus 3i plus 3i squared. Remember that I squared is negative 1, so we'll have negative 1 plus 5i in the numerator. And in the denominator, 1 minus I times 1 plus I is going to be 1 squared minus I squared. And since I squared is negative 1, we'll have 1 minus a minus 1, which gives us 2. So the end result is that this is minus 1/2 plus 5/2 I. It's interesting to note that the set of complex numbers is closed under multiplication, closed under addition. It's an example of what mathematicians call a field, and it is also a vector space. Here are some problems for you to do in preparation for class. The complex number z equals 2 plus 2i, w is 1 plus 3i. Calculate z squared, plot z and z squared in the complex plane. Calculate each of these quantities, z times w, z times z bar, z plus z bar, z over w, and the conjugate of the quantity z over w. So write each of those quantities in the form a plus bi, whereas this is equal to 2 plus 2i and w is equal to this.